So let's look at a very interesting question where we can make mistake if we are not careful, right? Especially with regard to law of conservation of energy. Okay. So it says a bullet of mass 0.08 kilogram moving at speed v gets embedded in a block of mass 2 kgs, right? So as shown in the figure, right, we have a bullet which is shot at the block and basically it's moving with a speed v and gets embedded in the block, which is a mass 2 kilogram and hangs from a vertical with a string length 1.5 meters. Okay, the block and the bullet moves together and stop. So finally swings together and basically gets stops when this angle is given to be 34 degree and we have to find the value of V, right? So the very first mistake you can do while applying the energy conservation here, that you can say in this system, right, the initial kinetic energy is half into mass of this bullet into V square, and that will be equal to mgh, right, the final energy, but that will be wrong, right? Why? Because when you have this bullet embedding into this block, basically there is a loss of energy, right? So if you want to apply the law of conservation of energy here, right, the first thing you have to do is first calculate with what velocity this one is going to move after the collision, okay, which we are going to call it V final, and that because of this kinetic energy of this block, basically it will go up to a particular height h, okay. So with that, so our starting point will be really to find the what velocity this block and the bullet is going to move after the collision, okay, where only valid principle applicable will be law of conservation of momentum, okay. So law of conservation of momentum needs to be applied to find my V final, which is the starting velocity with which the block and the bullet and embedded, right, embedded will start to move after the collision or embedding, okay. So how we can find that? That is where we are going to apply law of conservation of momentum, okay. So during this process, when this embedding or collision happens, right, what is the initial momentum of the system? Initial momentum of the system, we will go to write my initial momentum of the system is going to the mass of the bullet, which is in this case 0.08, right, multiplied by V, plus the block is stationary initially, right, so that's 0. So my initial momentum 0.08 V, okay. And after the bullet gets embedded into the block, this is a mass which is going to be the mass of bullet plus mass of the block, and it's going to start with V final, right? So what is my final momentum of the system after the collision? It's going to the mass of the block, which is 2 kgs, plus mass of the bullet, which is 0.08 kgs, okay? And it is going to start with the V final, okay? So V final is our velocity after the collision, and these two quantities, the initial momentum and final momentum, are going to be equal. So this is going to be 0.08 V, and now we can find the value of V final, which is going to be 0.08 divided by 2.08, okay, multiplied by V, and this is going to be equal to 0.038 V, okay. So with this speed, actually it is going to start, okay, and we have found that speed. Now in the part 2, when this system starts with a m plus m, or the mass of the bullet and the block here, right? So both of the bullet is also there, right? So this is 2.08 kilogram. It start with the V final, right, speed, and goes up to a certain height h, okay, and stops, right? And this angle now is given. So now we can go to apply the law of conservation of energy, right? So after that collision has already happened, we can apply the law of conservation of mechanical energy for this system. So initially, what is the mechanical energy of the system initial? That is again half into 2.08, right? Because now the bullet is embedded inside, into V final square, okay. V final square, V final we have already calculated, so we can put it over there and we can find whatever that number is, okay. And what is going to be my final mechanical energy here? Final mechanical energy over here is going to be mgh, right? So remember, the bullet is already embedded, so this is going to be 2.08 m into G, we are going to take 10, and H, which is over here. Okay, and these two quantities will be equal to each other, right? Initial mechanical energy is going to be final mechanical energy. So let's do that. So half into 0.08 is also going to be 2.08 into 10 into H. Yeah, the mass cancels, you know that already, right? So this is going to be like that, and we can get H as a value which is 1 by 20 meters. Okay. Now all we need to find is the value of H, and we are going to put it over here to get our answer. Fine. So we can do that, right? By finding the H using geometry, right? So what is the mass, the H is there, right? Into Vf square. Okay, we find the square. So this will be V find the square divided by 20. Right? So that's our H, and we find and we know the value already. Okay. So my H is going to be V square by 20. So what is going to be H, right? So H we have to find using geometry. Now, if you look at this triangle over here, let me do that in a different color, right? We are going to find this height H. First thing first, this height is equal to the length of the spring, right? This height or this length is also the length of the string which is attached to the block. So this height which remains here is going to be L cos theta, right? Right? This is L cos 34. Fine. So how much is going to be my H? H is going to be the total length from here to here, which is L minus this height. Can you see that? It will be L cos 34. Okay. So L we can take out common, which is 1 minus cos 34. L has a value which is 1.5, right? Into 1 minus cos 34 is 0.829. Okay. And that is our H. Now we can put it over here and we'll get, so let me write 1.5 into 1 minus 0.829, right? Is going to be equal to Vf square by 20. So we find the square by 20. So this will go on that side. So this is 20 into 1.5, that will become 30 into 1 minus 0.829 and the Vf square, right? And Vf square in terms of V, we have already found out, right? This is the one. Okay. So 0.038. So 0.038 square into V square. Okay. And all we are looking for in this question is this final value V, right? So this is what we are looking for, right? So we are going to take everything on the other side. 30 minus 1.829 divided by 0.038 whole square, and that's V square, right? And roughly when you do this calculation, right, the V square is going to, so my V is actually going to be equal to root under approximately 3600, right? So when you do that, you get 3600 something, which means my V is around 60 meter per second. Okay, and that's how we solve this question. This is a very important question for the exam because this embedding thing is usually seen in the exams, right? So again, going back to how did we solve the problem, the first thing we have to be careful here that we cannot apply the law of conservation of energy directly from the energy of the bullet to this final point, okay? Because there's a loss of energy here in the collision, okay? So loss of energy happens here in the collision. So we can only apply law of conservation of energy when we have this final velocity, right? Or the final kinetic energy, which is half m Vf square, where m is 2.08, right? Which includes the bullet, right? So to find this Vf, basically we use the law of conservation of momentum, right? And basically we found the Vf in terms of V, which is 0.038 V, right? And then we apply the law of conservation of energy part 2, right? To half into m into Vf square is equal to mgh. Okay. So my h comes to be Vf square by 20, and then we solve for it using the simple arithmetic, and basically we can get our answer to be 60 meter per second.